In Lab 2, we analyzed the movement of a falling object. When a ball was dropped from rest, the interactions between the ball and its surroundings can be incorporated into Newton's second law to better model the movement using software. In Fnet, equaling the sum of the forces, which also equals mass times acceleration. If Fnet is 0, acceleration is also assumed to be 0. Conversely, if net is non-zero, acceleration will also be non-zero. When analyzing a falling object, it is important to incorporate the force of gravity, which is 9.8 in the negative y direction. When using software to collect and analyze data, we use Tracker to analyze the experimental data that was extracted from video. We can see that the ball moved in the downward direction for about 0.633 seconds and traveled about 2.3 meters. With that, we can also see using VPython that simulations can produce varying forces. In one instance, Fnet was equal to weight. In another instance, Fnet was equal to weight plus the force of drag, which is proportional to the velocity squared. Both the force of weight and the force of drag were in the y component of a unit vector. We can see here that using VPython that the ball was simulated to move in the negative y direction with increasing velocity. However, in this model, the drag was very minute, so the arrow itself did not show. And that can be discussed later on in this presentation. But all three sources of data of Tracker and the two instances of VPython simulations were used to make this graph, in which the blue is equal to experimental data, the green is equal to the model with only incorporating gravity, and the orange was the model data incorporating gravity and drag. As you can see here, the experimental data moved about 2.3 meters as said before, but the simulated data only moved about 1.9 meters. This is due to there being an issue in finding the mass of the ball used. The ball was very light, so the mass itself had to be estimated. So this parameter affected the calculations, such as weight force, which the model data of simulations that we got from VPython was very reliant on the force of weight. So this is why these seem to move a lot less than the experimental data. So what does it mean to reach terminal velocity? Terminal velocity is the velocity at which opposing forces reach the same magnitude. So the net force equals 0. When net force equals 0, as said before, ma is also assumed to be 0, so acceleration stops. At this point, the velocity does not change, and the object, which is usually falling, stops accelerating. We can analyze the acceleration of models using the slope of velocity over time graphs. We can see that the orange line corresponds to the model as used before with respect to gravity, and the red corresponds to the model that incorporates gravity and drag. We can see here that the slopes of both are becoming more constant, meaning that acceleration is becoming more towards 0. This is especially apparent in the red line, which is becoming smoother. However, since gravity does not have an opposing force, it continues to be in the downward direction. So acceleration is 9.8 because of gravity, and the acceleration is becoming more towards 0 in the model that incorporates both gravity and drag. So, do any of these models predict terminal velocity? Well, in this case, when you look at the graph, neither have approached terminal velocity at this time frame. However, if the balls were to travel far enough and for a longer period of time, they could in fact reach terminal velocity for the model that both incorporates gravity and drag, because these two forces will cancel each other out and make acceleration go towards zero. So, if the ball was thrown rather than dropped, it would carry an initial velocity in the negative y direction, and the ball would travel further in the same amount of time. But if the ball was thrown, terminal velocity would still have the same value. However, since the ball had an initial velocity, the ball will reach its terminal velocity in a shorter amount of time. In conclusion, we were able to use Newton's second law to manipulate and describe interactions between the ball and its surroundings. The simulations were used using VPython, and the relationships of opposing forces were incorporated to predict the future, in this case, terminal velocity.